Okay, in this lesson we are going to be reviewing different methods for solving quadratic equations. We're going to start with the factoring method. If needed, you may want to pull out your factoring notes, and hopefully you've already watched the lesson video reminding you of different factoring techniques. Solving a quadratic equation by factoring is a quick, easy way to solve a quadratic equation, but it only works when we have real roots, and most of the time real rational roots. So the first step in solving by factoring is to set our equation equal to 0. The second step is to factor completely. So that's where you're going to have to think, am I factoring a binomial, a trinomial, or 4 terms? So starting with this first example right here, this is a trinomial. It does not have a greatest common factor, and it has a leading coefficient of 1. So the next step is we would create our sets of parentheses. We're going to put an x in front of each one because x times x is what gives us x squared. And then we are looking for the two numbers that multiply to -16, but add to +6. And so those factors would be -2 and +8. So we pop those in there, -2 plus 8, and this is still set equal to 0. Step 3 is we set each factor equal to 0. So x minus 2 equals 0, x plus 8 equals 0, and solve. So for the first one, we would add 2 to each side, and we get x is equal to 2. And the second one, we would subtract 8 from each side, and we get that x is equal to -8. And we know that if we were to graph the related quadratic function, and we take the equal 0 off and set this equal to y, that our parabola would cross the x-axis at +2 and at -8. Okay, so try the next one. Pause the video. When you're finished, start the video back. All right, so in the second one, we add 25 over. We then factor completely. We get the factors x plus 5 and x plus 5. Since they are the same factors, we only need to set the equal to 0 once because we're going to get the same answer twice. And what we call this one, we call it a double root, because if you were to set both factors equal to 0, you would get -5 twice. Graphically, what that means is instead of the parabola passing through the x-axis at 2 unique places, it only touches the x-axis once. And it means that the vertex, or that turning point, sits right on the x-axis at that value. So you might hear me refer to it as a double root or a multiplicity of 2. All right, so looking at the next one, if we use that factoring technique, again, we would subtract that 49 over first. So this gives us 16x squared minus 49 equals 0. Remember, we should always look for greatest common factor first, but in this case, we do not have a greatest common factor. So since it's a binomial, we then look to see if it is a difference of perfect squares. And it is, so we create our two sets of parentheses. We take the square root of the first term and put it in the front, so that would be 4x and 4x, and the square root of the last term and put it in the back, one being positive, one being negative. So that's +7 minus 7. And that's when we FOIL back, that +7 times -7 is what gives us that -49. 4x times 4x gives us 16x squared, and the outer and inner of +28x and -28x cancel, which is why this is a binomial and not a trinomial. We're going to then set each factor equal to 0 and solve. And so when we subtract 7, divide by 4, we end up with -7/4, and the other one we would add 7, divide by 4, and we end up with +7/4. So just like the factors look almost the same, except one's positive and one's negative in the middle, the roots are the same. They're the same root, except for one is positive and one is negative. We can also solve this one by using a square root method instead of a factoring method, since it doesn't have that linear term. So in this case, what we would do, since it's just got the x squared, is we'd isolate the x squared first by dividing through by 16. So that would give us that x squared is equal to 49 over 16. And then to get x by itself, we would take the square root of each side. The only thing about using this method is you've got to remember your plus or minus anytime you use that square root property. So we have to put plus or minus, and then the square root of 49 is 7, the square root of 16 is 4, and you can see we get the same answers. If you lose the plus or minus, you've lost half of your problem. And you got to remember that this quadratic function if you were to graph it, it does cross the x-axis in two different places. There are two solutions here. All right, so then we're looking at the last one. Some of you are able to factor this one by just guessing and checking, and that's great if you have really good number sense and you're able just to kind of sit there and think it out. Okay, well, is this going to be 4k and k? What could I do to make this work? Well, could I make that 1 and 9? Okay, yep, that would work out there, and I want that to be negative 35, so that would make that negative 9, so that's negative 36k. I'd make that positive 1, so that's positive 1k, which adds that negative 35k. And if you're able to do that, that's great. If not, you may need to do it the long method. And the long method is where we use that AC product. So we would say 4 times negative 9, and that gives us negative 36. And then what we're doing is we're looking for the two numbers that multiply to negative 36, but add to negative 35. So if we go through our factors of 36, it would have to be 1 and 36. We know one of them needs to be negative, and to make it work, that would be negative 36. So we would rewrite this as 4 terms, because remember, when you FOIL or box, you have 4 terms before you make it into that trinomial. So that'd be 4k squared plus 1k minus 36k minus 9. We then use our grouping method. So what does 4k squared plus 1k have in common? They have k, and we're left with 4k plus 1. Over on the other side, we know we have to factor out a negative, and then what divides evenly into 36 and 9 would be negative 9 there, and that would then be 4k plus 1 when we factor that out. So our common group is 4k plus 1, and when we factor that out, we're left with k minus 9. And again, the order we write those factors in really does not matter. Once we get our factors, we then set each factor equal to 0, and we solve. And so for this first one, we would subtract 1 and then divide by 4, and we get k is equal to negative 1/4. Please do not skip those steps if you make mistakes. I would rather see you write out the steps and get it correctly. In the second one, we would add 9 over and get k is equal to 9. So in this case, we have 2 real rational roots if we were actually thinking about the related quadratic graph of the parabola. All right, so for the next part, we're going to practice completing the square. Probably most people's least favorite method, but it's good that we go back through it because we have to know how to complete the square in order to put a quadratic function from standard form to vertex form, and we're also going to be using completing the square with circles later in this unit. So refer to the sheet that has the factoring steps on the front side. On the back side, it has the steps for completing the square, and we will walk through these as we go through this. Step 1 for completing the square is to set your equation equal to 0. Step 2 is to make sure your leading coefficient is 1, the coefficient of x squared. And if not, you have to divide through by whatever that number is. Step 3 is to move the constant term to the other side. So I'm already at step 3. My leading coefficient is 1, my constant term's on the other side. So what I'm going to do now is, we know the whole idea for completing the square is we want to make this this left-hand side into a perfect square trinomial so that we can factor it into a binomial squared. So what I'm going to do is go ahead and set this up, and because we're going to add something to make this a perfect square trinomial, what we do to one side we must do the other. So I'm going to add these blanks on both sides. All right, then what we do is we take half the coefficient of the linear term. Half of negative 6 ends up being negative 3. We then square it and put it back. So negative 3 squared is positive 9. And anytime you square a positive number or a negative number, it's always going to be positive. So that's why I already have that plus there. So we have x minus 3 quantity squared, and then on the right-hand side, that is equal to 49. As you can see here, if you were to factor x squared minus 6x plus 9, it would have 2 equal factors of x minus 3, x minus 3. Once we can get this into a binomial square, we can then apply our square root property and use the square root method that we used above. So what we would do is we would take the square root of each side. But remember, anytime you apply that square root property, don't forget your plus or minus. So that is going to be x minus 3 equals plus or minus, and then the square root of 49 is 7. And then to finish this out, different people do it different ways. I just add the 3 over and then work it out. So I say, okay, well, that's really 3 plus or minus 7. And then I know that 3 plus 7 would give us 10, and that 3 minus 7 would give us negative 4. So in this case, we have two real rational roots of negative 4 and 10. All right, so pause the video, try the next one. Pause now. All right, so in this case, we have a leading coefficient of 1 again, which is nice. So we're going to subtract that constant term to the other side. We're going to move it over, so that's going to be x squared minus 4x plus blank, because I want to leave a blank where it originally was, equals negative 1 plus blank. Remember, golden rule of working an equation, what we do to one side, we must do to the other. Then we go ahead and set this up. We know we're going to create a binomial squared here. To do that, we take half of the coefficient of the linear term, so half of negative 4 is negative 2. We then square it and add it back to each side. So that then gives us x minus 2 quantity squared equals 3. At this point, we can now apply that square root property. What we do to one side, we must do the other. Don't forget your plus or minus, so we get x minus 2. It pops out, it undoes that square, equals plus or minus the square root of 3. We would then add 2 to the opposite side, so we get x equals positive 2 plus or minus the square root of 3. So we have two different roots here. One is 2 plus the square root of 3, and the other is 2 minus the square root of 3. I'm fine if you write it with just the plus or minus. I just want you to understand that there are two roots. Notice in the first one we have two real rational roots, but in the second one we have two real irrational roots. Okay, so I went ahead and did the next two for just time's sake. This is why we don't really all love completing the square unless we just love the algebra, because it gets a little bit messy. When we look at number 3 doesn't have a leading coefficient of 1. So the first step is we had to divide that whole thing by 3. And then it creates all these fractions. So it's the same steps over and over again. You set up your binomial squared. You take half the coefficient of the linear term, so half of 5/3. You can see where I worked it over to the side is 5/6. We then square it and add it back to each side, so that's 25 over 36. Well, then over here on my right-hand side, I had to get a common denominator, so the least common denominator was 36, so negative 4/3 is negative 48 over 36. When we add it, we get negative 23 over 36. At this point, we can take the square root of each side. Negative 23 is not a perfect square, and 23 is a prime number, but because it's negative, we can pull the I out, and then we're left with the square root of 23, and then the square root of 36 is 6. When we subtract the 5/6 over to the right-hand side, we notice we have a common denominator, so we can join that all together and get the answer is negative 5 plus or minus the square root of 23 all over 6. And you can notice in this case, we end up with two complex imaginary roots, where in the last one we ended up with real roots, but one set was rational and the other set was irrational. So hopefully in the previous course you spent a day or two working with completing the square. So I'm not going to spend a whole nother day on just completing the square, but what you realize when you do learn how to complete the square the first time is that it's the same steps over and over and over again. So why not just do that to our basic formula for a quadratic equation in standard form? And that's what we see me doing in number 4. And by doing those steps, but doing it with those letters A, B, and C, we derive the quadratic formula. And the quadratic formula is just so much easier to use, and it comes from completing the square, because then you don't have to get stuck doing all this fraction work like we had in number 3. All right, so for each of these on the back, we are going to solve each equation using the quadratic formula. Remember, anytime you're using the quadratic formula, the first step is you have to set it equal to 0 before you pick out A, B, and C to substitute into our quadratic formula. All right, so with the first one, we need to subtract 18 from each side and set this equal to 0. So that is x squared minus 7x equals, minus 18 equals 0. All right, we are then going to pick out our A, B, and C and pop it into our quadratic formula. So remember, when we're looking at this, we're looking at ax squared plus bx plus c equals 0. And on your reference sheet, you've got the quadratic formula song. It goes to row, row, row your boat. If you have a hard time remembering the quadratic formula, that's a good way to remember it. You can sing it in your head as you pop it in. So we have x is equal to the opposite of b, which would be positive 7, plus or minus the square root of b squared. And y'all, I always do that in my head. I never write right here negative 7 squared. Go ahead and square that in your head. And remember, anytime you square a negative number or a positive number, it will always be positive. So that'll be 49 minus 4 times a, which is 1, times c, which is negative 18. All over 2 times a, so that's 2 times 1. All right, so then we're going to clean it up. So that is 7 plus or minus the square root of 121 all over 2. 121 is a perfect square, so that is 7 plus or minus 11 over 2. So we then break it up. 7 plus 11 is 18, and 18 divided by 2 is 9. 7 minus 11 is negative 2, and is negative 4. And negative 4 divided by 2 is negative 2. So in this case, we have 2 real rational roots, negative 2 and positive 9. So this one actually would have been one that would have been easy to factor. If you had used the factoring method, the factors would have been x plus 2 and x minus 9, and then you could have set each factor equal to 0 and solved, and you would have gotten negative 2 and 9, which probably would have been much quicker. Let's look at the next one. So the next one's already set equal to 0. So we have our a. Remember, a is always the number in front. You got your a right here, b, and c. We're going to pop into the quadratic formula. So we have x is equal to negative 9, opposite of b, plus or minus the square root of b squared. So 9 squared is 81, minus 4 times a, which is 1, times c, which is negative 11. All over 2 times a, so that's 2 times 1. So that gives us negative 9 plus or minus the square root of 125 all over 2. All right, in this case, 125 is not a perfect square, so we want to see, is there a perfect square other than one that divides into 125? And there is, because 125 is 25 times 5. So if we think about that, if we take the square root of 25 so that it can come out, that is going to give us negative 9 plus or minus 5. And then we can't take the square root of 5, so that 5 stays inside, all over 2. So in this case, we have 2 roots. One is the one with the plus, one is the one with the minus. But you'll notice that they are irrational roots this time. They are real irrational roots. All right. For the next one, I would multiply it by negative 1 first. It just makes it a lot easier if that leading coefficient is positive, because then you don't end up with a negative in the denominator. So if we multiply this whole equation by negative 1, we'll make that positive 3x squared minus 4x plus 4 equals 0. Now what I would like for you to do is pick out a, b, and c and use the quadratic formula. See what you come up with. When you're finished, start the video back. Pause now. If we've set this correctly, we should get down to 4 plus or minus the square root of negative 32 all over 6. Again, 32 is not a perfect square. Also, we have a negative in this one. So we want to find the largest perfect square that goes into 32. And y'all got to know this perfect squares: 1, 4, 9, 16, 25, 36, 49, and so on. So the largest perfect square that goes into there would be 16. So I'm going to say negative 16 times 2. The fact that it's negative, when we take the square root of it, we're going to pull an I out with it. So that's going to give us 4 plus or minus 4i. The square root of negative 16 is 4i. And then that 2 has to stay inside, all over 6. Once we get to this point, because the coefficient in front of this square root and this 4 right here and the denominator are all divisible by 2, we can reduce it. But we never ever reduce until the very last step. So since all of those are divisible by 2, we would say this is 2 plus or minus 2i square root of 2 all over 3. The 2 inside the square root does not reduce. We cannot reduce stuff inside a square root with numbers outside the square root. So we'll notice in this case that we end up with 2 complex imaginary roots. So here's where the discriminant is important. The discriminant is the part under the square root. And if you look at each one of these, The first one we had 121, which was a positive perfect square. The second one, the discriminant is 125, which is positive but not a perfect square. And the third one, the discriminant is negative. So how does the discriminant help us? If the discriminant is a positive number, that's what this part means right here. If it is greater than 0, so it is positive, and it is a perfect square, we're going to always end up with two real irrational roots. And graphically, that parabola is going to intersect the x-axis twice. If it is positive, but it is not a perfect square, then we're going to end up with two real irrational roots, which also intersects the x-axis twice. But if the discriminant is negative, and it really doesn't matter if it's a perfect square or not, we're going to have two complex imaginary roots. Whether it's a perfect square or not doesn't matter, because once you pull that I out, they're imaginary. And graphically, what that means is it does not intersect or touch the x-axis. And the last situation is, what if the discriminant is 0? Well, if the discriminant is 0, what's going to happen is you're going to end up with plus or minus 0, so you're only going to end up with one answer, and it's going to be one real rational root. And that's the situation where you have that double root and your vertex, your max or min, sits right on the x-axis. And that vertex, that root, is the same thing as the axis of symmetry, because that's what we're left with. All right, last part of our lesson. How do we write quadratic equations given the roots? Well, folks, what you have to do is you have to work backwards. You pretty much do the exact opposite steps of what we did when we were solving by factoring. So if we think of these being our roots, really what we had is we had x equals -2, and we have x is equal to 7. So if I set those back equal to 0, that means that I had x plus 2 equals 0, and x minus 7 equals 0. Well, if I then put them back together as they were as factors being multiplied before we broke them up and set them equal to 0, that is x plus 2 times x minus 7 equals 0. At that point, you can then FOIL or box, however you do it. So we would have x squared minus 7x plus 2x minus 14 equals 0. And we'd put it all together to be x squared minus 5x minus 14 equals 0. And that would be the quadratic equation that gave us those roots. All right, pause the video, try the next one. For this one, I'm going to get rid of that fraction from the beginning by multiplying each side by 3, and then getting the factor 3x minus 1, because I don't want to have to multiply this all out with x minus 1/3 and do all that fraction work and then get rid of it at the end. Go ahead and get rid of it in the beginning. So our final answer should be 3x squared minus 16x plus 5. All right, very last problem. Find the value of k that makes the statement true. -1 is a root of the following. All right, a couple of different ways to do this, but I'm going to go straight forward to the quickest way. Guys, if they give you a root, that means that when you substitute that root in, it should make that equation true. It should make this equation set equal to 0, because remember, a root is the x-intercept. And when you have an x-intercept, the value of y is 0. And what this function is equal to is y. So to work this out, all we have to do is substitute -2 in wherever we see x. So that is going to give us 2 times -1. I'm sorry, I think I just said -2, but I meant to say -1 squared minus k times -1 plus 3 equals 0. So we're not going to work that out. Remember, exponents always before multiplication, so that's 2 times +1. Negative times negative is positive, so k times 1 is k, plus 3 equals 0. So that would be 2 plus k plus 3 equals 0. So that's k plus 5 equals 0, and we get that k is equal to -5. And if you wanted to check it, you could always rewrite that equation. And so if we were just checking, that would have been 2x squared. Well, since it says minus k and k is -5, minus and negative would be positive, so that would be plus 5x plus 3 equals 0. If you factored this correctly, those factors would be 2x, x in the front, and then we'd have to put the 3 here, 1 here, everything's positive. So those factors would have been 2x plus 3 and x plus 1. And if you set those factors equal to 0, you would have had x equals -3/2 and x equals -1. And yes, -1 is a root.